Hello, this is Professor David Clough with you for a series of boot camps or workshops on MATLAB. And this is the first of these, getting up to speed or back up to speed with MATLAB. I will mention at this point in time that there are two parallel series of boot camps. One based on the Python programming language, and then the second based on the Excel spreadsheet and companion VBA programming language. Though all three of the bootcamp series follow the same format, and in bootcamps 2 and 3, they use the exact same examples. So this will be the one on MATLAB. Many students have been exposed to MATLAB early on in their college careers and then may have been away from it for some point in time. So the first boot camp here is meant to help you have a refresher on the use of MATLAB, and will likely also include some features that you haven't seen before. And also in double purpose, this first boot camp can be used by somebody who really has no exposure to MATLAB and needs to get started. You'll see here the outline of this first boot camp, working our way through the MATLAB package and its features and its programming. And then when we move on to the second boot camp, we will solve, using MATLAB, a series of typical chemical engineering problems that are have different character, but they're of fairly small scale. And then we move on to the third boot camp, where we take a look at the modeling of two chemical reactors, where it's somewhat more complex, and it calls on us to pull together much of what we've seen from the first two boot camps. So this is where we are, and just to get started here, you need to install MATLAB on your computer, because if you sit back and watch what I do here and do not participate, you are probably not going to get very much out of this. So this just, for the University of Colorado, gives you an idea of where you can find the MATLAB package for installation on your own computer. And as you do this, MATLAB installation provides you the opportunity to select a series of supplementary toolboxes. And there are many, I believe there are over 100. And so what I've listed down at the bottom are the ones that are typical that we need or would use in engineering calculations, especially in chemical engineering. So although you can install all the toolboxes, which will require a fairly lengthy installation, take up quite a bit of your memory, disk memory, the ones listed here give you the ability to make a more tailored installation. You might want to consider that. So when you launch MATLAB, you're going to get a frame that looks like this. The current version that I'm using, that is the basis for this boot camp, is the 2024A version of MATLAB. There are new versions issued every year, usually not with dramatic changes. And so this is the latest one at the point that I'm recording this video. And MATLAB's been around a long time. It's been around 50 or so years. It was a product pioneered by a person by the name of Clough. And you can read some interesting facts about him at that link noted on the slide. And I have used it myself over the entire period, a 50-year period of time. It was originally based on the Fortran programming language, and then it evolved into its own script language as the years went forward. So when you do launch MATLAB, you get a main window that looks like this, and I pointed out some different areas that will be of interest to us. The file directory over on the left, which will show you what script files you have in the path that is denoted up here, the current path. There is a ribbon which has many drop-downs and many commands available. And the main command window is here. And then there is a workspace here that shows our variables and gives us the ability to view their current values. In addition to this, we make use of an editor window to produce scripts and save them in files. And the files have an extension of the letter M. They are text files, but they have an extension of .m. So you can take a look at the extent of your installation in the command window by issuing the ver command, which is short for version. And it will give you what the current version is that you're using. And then it will also give you a very lengthy list of all of the elements or toolboxes that you have available to you. If you have installed all toolboxes, that will be a very lengthy list. And quite frankly, you will have installed many, many toolboxes that you will never use. So back to the command window, and I'm going to pop over to that now to take a look at it live. Looks something like this, and you'll notice I have a very lengthy list of files here. These are the files that are relevant to Bootcamp 1, and they are all available to you in a zip file associated with this bootcamp. This is of particular interest with the longer scripts where we don't want to take time during the bootcamp typing in an extensive amount of information. For shorter examples, I will tend to type them in myself, and I recommend that you do the same. So one thing that we can do here is that if we're in the command window, we can click this little guy up here and we can undock it. You'll notice the shortcut for that is Control-Shift-U, and then it becomes a floating window that we can move around, or we can dock it with Control-Shift-D and it puts it back where it was. I don't usually float or dock these menus. I pretty much leave this integrated development system as it appears. But that just gives you an idea, and you can do that with any of the windows that you see there, all four of them. So with the command window, we can enter commands one by one there and see a result. So just as an example, I'm going to start with a parenthesis and use sqrt for the square root of 5 minus 1, right parenthesis, divide by 2. And it shows me in 4 significant figures, 0.6180, which is the golden ratio. And if I would prefer, this at the moment is stored in a generic variable over here called ANS for answer. But if I wish to create this and store it in a variable name, what I'm going to do here, you can't see, is I'm hitting the up arrow, and that brings back the last command. And then I'm going to go over to the front end here and type gr equals, all right? And then I'm going to go to the end, and I'm going to put in a semicolon. And when I hit enter there, nothing shows in the command window because the semicolon says to suppress that kind of output that we saw up here. But over here in the workspace, we see there's a variable gr, and it has the value 0.6180. Of course, there are many more decimal places to that. That is just what is displayed. There are 15 to 16 significant figures for a numerical quantity that is stored by MATLAB. Now, if I want to, if the command window is getting cluttered with past things, I can type CLC, and that will clear the command window. I can type clear, and that clears the workspace. And then there is a command history down here that keeps our previous commands. And up in the variable group here, if I drop down clear workspace and ask it to clear all functions and variables, it will do that, all right? I also have the ability to clear the command history over here. If I do clear commands, command history, and answer yes, that wipes out my history of commands. So at this point, it doesn't allow me to go back to previous commands. The other thing you may have noticed when you go and you bring up a previous command and then you edit it, you can edit it anywhere in the line, and your cursor does not have to go to the end of the line before you hit the enter key. All right? So retrieving previous commands with the up arrow, and by the way, you can go back more than one command to get like the command that you did 3 or 4 lines ago. All right. So if we're going to, instead of working with commands in the command window, if we are going to create a script, which we most frequently do, then we are over here and we can say that we would like a new script, all right? And then we get our editor window here, which is floating, and we can move it around. And this is where we put in a script, and it's got a file name currently called untitled, and we can save it under a different file name, and it will automatically have an extension .m. So the editor works very much like any simple text editor like Notepad or WordPad. The way you move around and how you copy and paste things and erase things is very similar to that, all right? So what I can do here is I can put in that one command that I had, gr equals let's open with a parenthesis, sqrt 5 minus 1 by 2 with a semicolon to suppress output. That is now a script, and the name up here, untitled, has an asterisk by it, and that's a reminder that we have not saved the script when when changes have been made. And up here, this little diskette symbol is highlighted blue. So if I create a name here called golden ratio and hit enter, that now saves it in the script name goldenratio.m. And you'll notice the little diskette symbol up here is grayed out because the version that's saved is the same as the version that's present in the editor window. So that's a little bit with getting started with that. We're going to go back to the slides and review that. And then we'll deal a little bit with the elements of the expressions that you make, the mathematical or arithmetic expressions that you create in MATLAB. So let's pop back over to our slide. This reviews undocking and docking, and you've got your shortcuts there. Control-Shift-U for undock and Control-Shift-D for dock. And you have to have that particular window selected when you make those operations. And then here we're just reviewing, putting in an expression and getting an echo answer, or using the semicolon, assigning to a variable, and not getting an echo on the command window, but it's showing up in the workspace. Clearing commands, we can do that from the ribbon. We can also just type in CLC, and you can clear all your functions and variables with the clear command, or you can do it based on the clear workspace drop-down menu. You can retrieve previous commands in the command window by using the up arrow. But you cannot move up to a previous command in the command window with your cursor and execute it there. You have to retrieve it by using the up arrow. Then you can edit it anywhere and hit enter, and it will show up for you, okay? And your command history will show this particular thing and here, and you can dock it using Control-Shift-D, and it will show up in the lower right corner of your MATLAB overall window. Opening an editor for a script over here on the left with new and selecting script, and we get a script called Untitled, and we can open multiple scripts using the menu, or we can use the plus sign here, and we can have multiple scripts created. We can also retrieve and display multiple scripts, and you will see along the way that we do that. So the text editor we show you here, and you'll become more familiar with how to use that and test your scripts as we go along through the boot camp. And here we're saving a script. This one shows, call it golden ratio, and we click save, and it gets saved into the file path or directory that we have listed in the upper part of the MATLAB window. So getting on to MATLAB expressions, things here are fairly conventional. Expressions are evaluated left to right. You can modify that priority by enclosing parts of expressions in parentheses. And functions and expressions are evaluated first, like that SQRT for square root is evaluated before anything else in the expression. The arithmetic operators look like this, and the main one to be aware of here is exponentiation, which uses the caret or the shift on a 6, and you'll notice that it has the highest priority, and it in a combined expression, it will be the first of any of these operators that gets evaluated. Just as a comment, you have to be a little careful with this, because when you go to something like the Excel spreadsheet, it actually reverses these first two, and it does negation before exponentiation. And then if you go over to something like the Python programming language, it uses a double asterisk for exponentiation and not the caret. And this over here just shows you a few examples of that. Minus 3 to the power 2. First squares 3 and then applies the negative. All right. Here is 3 by 2 times 4. So it does this left to right. 3 divided by 2 being 1.5 times 4 being 6. And that means that you can actually repeat that. 3 divided by 2, get the result, and divide by 4. If you would like to force the 2 by 4 into a denominator, the way it's written, you can enclose it in parentheses, and it will become the denominator. For relational tests that yield a true-false result, which in MATLAB is either a 1 or a 0, you've got testing equality with the double equals, and the rest of these are pretty self-explanatory. The only one that is again different here is not equal, has the less than and greater than put next to each other. So that's how do you do not equal. There are logical operators like not, and or, and we may see those later on in our boot camps. So that is enough of that, and we're going to go back over now and talk about arrays, vectors, and matrices in MATLAB. So let's go back over to our command window. MATLAB stands for Matrix Laboratory, and it was built originally to help us in making numerical calculations with vectors and matrices. So it is particularly strong in its abilities to do that, as you will see. I can, for instance, show a row vector as something like 12 minus 3 in 5 and 97.6. And you'll notice that that is surrounded by brackets, and if I hit enter, it shows that as a row vector or a row array. If I come back to that with the up arrow and put in semicolons between the first three items here, and hit enter, then it shows as a column vector, because the semicolon indicates essentially go to the next row each time you see it. So that way we can do a row vector, or we can do a column vector. To expand upon that, we come along here and we can do a row like 14.2 and move to the next row, minus 3, minus 7, and move to the next row and do 0.6, for example, and minus 3.4. Put our end bracket there, and we get a 3 by 2 matrix or array, and that's how we can deal with that. So that gives you some examples there. And then we can go back and we can create a matrix and assign it a name. You don't have to use capital letters or uppercase letters for matrices, but a general convention is to use lowercase letters for one-dimensional arrays like the first two up here, and then use uppercase letters for two-dimensional arrays or matrices. So let me put one in here. A equals 14 and 2 in the first row, and -3 and -7 in the second row, and 0.6 and 3.4 in the third row. And then I'll put the semicolon out here so we don't see an echo. But you'll notice up over here on the right, we have an A matrix, all right? And it's shown here. And then I can use a little spreadsheet capability of MATLAB by double-clicking this little spreadsheet here. And it shows the matrix on a spreadsheet with the elements, and we can actually go in here and change a value. We can observe the values, and when we're done, we can just X that out. You may have noticed that when I hovered on A, it said it's 3 by 2 double. That means 3 rows by 2 columns, and double means double precision, floating point number, or a decimal number with 16 significant figures. So that's a little bit about creating a matrix in the workspace and looking at it using that spreadsheet feature. So to bring everything back up to the top, I'm going to do CLC to make it a little more visible to you. And we'll create some vectors using the colon operator. So I'm going to say x is equal to 1 colon 5, and that gives us a vector with intervals of 1 from 1 to 5, all right? And then I can do another one, y, which is equal to 5 colon -1 colon 1. And what I've done here is I've said I want to go to 5 to 1, and I've put the interval or step in between the 5 and 1. I didn't do that up here, and the default is then +1. And this takes us from 5 and counts down to 1. All right? And then further from this, I can create another x vector equal to 0. And for instance, in steps of 0.2 to 1, and that shows going, doesn't quite fit on the screen, but it shows my row array or vector with those steps. And then likewise, I can try something a little different here, and I can say go w equals 0 in steps of 3 to 7. And you'll notice, of course, 7 is not going to be on a step of 3, so it goes 0, 3, 6, and then it doesn't give us anything beyond 7. So that's a little bit with the use of the colon operator. We'll see that again when we deal with arrays and matrices. So let me clear that out. And then we can use some built-in functions like A is equal to linspace of 0, 10, 11. And the way that you read that is we're going to, between 0 and 10, we are going to have an 11 equally spaced values. So when we do that, we get the counting numbers 0 to 10. Another thing that we can do is a little bit different, is that I can change that. And by the way, I'll mention that I'm not going to show the output, but if I went B is equal linspace 0, 10 with no number of items, put in the semicolon and hit enter. Over here, if I look at B, it shows that we have 100 items, a 1 by 100 array. So the default in terms of the number of items that you have between 0 and 10, if you don't specify it, is 100, all right? So you want to keep that in mind. And then an alternative to this for the original one back there is that instead of linspace, we put in log space, all right? And we go 0 to 1. And what we get is a set of numbers from 1 to 10, which are spaced equally by their logarithm base 10. The 0 and 1 here correspond to exponents of 10, 10 to the 0 being 1, 10 to the 1 being 10, and 11 are the number of points equally spaced by logarithm between those two. As chemical engineers, we do not use log space that much, although we use it quite frequently in work in process control systems. Okay, so that gets us with linspace and log space, and let me clear this out, and we'll start over by clearing our workspace, CLEAR. That clears the workspace. And then I'm going to go back and we're going to talk about how you reference elements in arrays, individual elements. And so I'll set up our A matrix again. And you'll notice when you set values, you use brackets when you set values in arrays. So I'll put in 14 and 2 in the first row. And by the way, you can separate the 14 and 2 by commas if you like to do that. It's not necessary. A space is okay. -3, -7. You don't have to use a lot of spaces. I tend to use them to make things read a little more easily. So there's an A matrix, which is, as you'll notice here, it's 3 rows by 2 columns, all right? And then if I say, well, what is A 2 comma 2? It's -7 because it is the second row, second column, which you can see is this guy here, all right? I can also come back to my colon operator and say, what is A? And you'll notice I'm using parentheses here for these indices. If I do 1 comma colon, that says row 1, all columns. The colon means all columns, so we get the first row. If I do A 2 comma, colon, comma 2, what it does there is it gives me all rows, the second column, all right? So you can sort of see that, 2 minus 7 minus 3.4. So that is a little bit on how we can index those things. Another way that we can handle this, let me clear this, bring it back to the top, is I can say B is equal to an array which is 12 minus 3, 5, and 97.6. And then I can say I would like to see B 2 to end. And it gives me the last 3 elements, where end just means go to the last element, go from 2 to the last element, all right? So you can use end in that way. That would have been equivalent to saying B is equal to 2 colon 5, right? B is equal to 2 colon 5. Okay, so we've got that. Let's move on and talk about how you can do mathematical operations with arrays. And of course, what you find is that because of the way MATLAB was designed, it is ideal for doing numerical calculations with arrays. In fact, it is an ideal package for doing all kinds of numerical calculations in science and engineering. Possibly the best package available anywhere. And so, of course, the downside of MATLAB, if you're outside the university, is that it's not cheap to pay for an annual license for MATLAB. So let us start here with A equals to an array 1, 2, 3, and 4. B is equal to 6, 7, 8, 9. And then if I just say what is A plus B, it what we call an array operation, adds 1 and 6, 2 and 7, 3 and 8, 4 and 9, and gets the results. Likewise, if I would say what's A minus B, it subtracts the items B from the items A, and it gets minus 5s all the way across, because that's the difference between each one of them. Now, when you do these kind of simple additions and subtractions, your arrays have to conform in terms of their size and their format. So if I start a C array here and make it equal to 5, 7, and 9, and then I say what's A minus C, it doesn't like that, and it tells us right away in red, which is the color used to indicate something bad has happened, is that the arrays have incompatible sizes for this operation. It's a relatively informative error message that we've got there. Okay? So let's move on and just discuss a few other vector matrix operations. If I say what's A plus 3, it's happy with that, because what it does is it simply takes the scalar 3 and adds it to each element of A. Nothing too fancy there. And if it can get a little bit tricky when we start talking about compatible vectors, either row or column. So if I redefine C here and make it equal to a column vector, which is 5, semicolon, 7, semicolon, 9, semicolon, 11. And then if I say what is A minus C, it'll work with that, because essentially what it will do is it will take the 5, 7, 9, 11, and then if we'll remember what A is, 1, 2, 3, 4, all right, and it will take minus 5, right, and then it will apply to 5, 7, 9, and 11, 1 to get the minuses there, and then in the second column it'll apply the 2, and then the 3, and then the 4. So that's a little bit tricky, because you might not think that those are acceptable for compatible dimensions, but it turns out that they are. Okay, so let's just recall we got A here, we've got B here, and one thing that we can consider here is let's make a column vector out of B, and we can do that by saying B equals B apostrophe, And what the apostrophe stands for is transpose rows into columns, and we'll review that again in a little bit. And then we can say, what is A times B, all right? A times B, and we get 80. And what we have done there, looking, let's bring A back for a second, is we've taken 1 times 6 plus 2 times 7 plus 3 times 8 plus 4 times 9, and we get 80. And the other way we could go is and so what we've essentially said there, let's review that, is that A is 1 row by 4 columns, all right? B is 4 rows by 1 column. So putting the B over here, the 4 columns here and the 4 rows here are compatible for what's called an inner product, and we get a result called 80. Now if we go to B times A, then we get a 4 by 1 times a 1 by 4, so the result's going to be a 4 by 4, and that's called an outer product. So we will review that here on the slides, and then show a couple of other operations using the slides that are useful to us, and we use them a lot. So let's go back to the slides. So this is just a review of the operations that we went through to show how to create a row vector, a column vector, 2 by 2 matrix, in this case 3 by 2, and then how we can assign that to a variable name, and then we can use our workspace and the spreadsheet button to take a look at those values and how they're laid out. Here is the use of the colon operator that we went through with you, so I won't spend too much time here. And then linspace and log space, and we did that, and it gives you the details here in the little blue boxes for linspace and log space. And then referencing the elements of vectors and matrices in terms of row column, 2 by 2, row 2, column 2, etc. And then using the end indicator, 2 colon end means all the items from the second item to the end of the vector. Adding and subtracting item by item, and you can't do it when they're not compatible. And you can add scalars or take them away, and then you can do this fairly tricky subtraction of a column vector from a row vector and get the kind of result that we showed here. Of the inner product of 2 vectors, and this is where it shows how this works over here. You've got an n column 1 row array, 1 by n, and an n by 1, and these two have to agree, and then you get the summation of the product of A1, A2, B2, etc., shown here with a summation formula, and that's called an inner product. And if you reverse that, then you end up with an n by 1 and a 1 by n, so you end up with an n by n. So here we have a 4 by 1, a 1 by 4, so we end up with an outer product being a 4 by 4. Okay, so that's how that works. And then we move on and we'll take a look at 3 additional operations that are common in linear algebra and numerical methods. The first of these is just the general situation with matrix multiplication, where here let's move along here. Here we're showing an A matrix which has m rows and n columns. And here is a B matrix which has n rows, matching the n columns here, and p columns. And it ends up in a product which has m rows and p columns. And here this shows by sort of taking the A row and pouring it down the B column here, multiplying the pairs and adding them together, how you get each element in the product matrix. And this shows the math down here of how that's done. And then over here it shows how the inner dimensions here of the number of columns, number of rows have to agree, and the outer dimensions are the dimensions of the product matrix. And then we show an example. So we can come back over and illustrate that here. Let's get back to our command window. And have an A matrix which is equal to 22 minus 3 minus 7 and 0.6 and minus 3.4. So there's our A matrix. It's 3 rows by 2 columns. And then we're going to have a B matrix which is equal to 5, 1, whoops, 5, and minus 4, 6, minus 8, minus 4, 6, minus 8. So here we have a B matrix which is 2 by 3. This is 3 by 2. So your inner dimensions 2 is going to drop out, and we should get a product which is 3 by 3. Isn't that right? And there it is. Okay? So you can see that we can do all these vector matrix operations with the standard operators like asterisk for multiplication. MATLAB supports that very nicely. Also, as we showed before, if you want the transpose of a matrix, you can just use the apostrophe, and it will take our 2 by 3 and make it into a 3 by 2, all right? So that is the use of the transpose operator. And we can also come back and remember what A is, and then do A transpose, and it looks where the rows become columns and the columns become rows. As you look at that, if we've got a little a vector back here, and recall that when you have variables in MATLAB, it does distinguish upper and lower case. So a capital A is a different variable from a lowercase a. So if I take something like A times A apostrophe, that is called the inner product of A with itself, and what it does is it sums the squares of A. So you got 1 plus 4 plus 9 plus 16, and you get 30. So that's how you can end up doing essentially a sum of squares of a vector. And then we'll take a look at a couple of special matrices that we want to use at times. One is the identity matrix, and there's a function for that called EYE. So if I do EYE4, it gives me a 4 by 4 matrix with 1s on the diagonal. And then if I would like to have a diagonal matrix with different values, I could come back here and say something like 3.5 times I4, and then it puts 3.5s on the diagonal, okay? So that's using the I function. And then we come to looking at what is the inverse matrix, because that comes up in calculations with linear algebra. And essentially, the inverse matrix is the matrix, it's only for a square matrix, and it's the matrix when you multiply it by the original matrix, it yields an identity matrix, okay? So the way that will illustrate that, and then we'll go back to a slide to show it again, is I'll come back and I'll define a matrix capital A as 1, 5, 6 for the first row, 2, 9, minus 1 for the second row, and 3, minus 7, 4 for the third row, all right? So we'll define the A matrix like that, and then what we will do is we will compute an inverse A matrix by taking A, all right, to the power minus 1. So that should be the inverse matrix. Now, a way we can check that is we can say, well, what's A times AINV? And you can see that is essentially the identity matrix. There might be a little numerical juggling in there, but it's the identity matrix, which means that AINV is indeed the inverse of A. Since this is done so frequently, another way to do this is that there's a built-in function in MATLAB. So you'll notice it's the INV function, and you'll notice that this set of numbers is the same as the one up here. So that's a little bit on the inverse matrix. Now, let's pop back over to the slides and catch up to that, all right? And so let's come back over here, move along. This shows the transpose, and the transpose of, shown here as an operator at the end of an array definition, and it can do it that way too, or it can operate on a variable to do the transpose. And this shows that A times A transpose is equal to the sum squares of the elements of A. And we illustrated that for you. This was the identity matrix using the EYEI function, and then modifying that to a diagonal matrix by multiplying it by a diagonal value, all right? And we went through that with you. And then we have the inverse matrix of a square matrix. And here we illustrated its calculation. And by the way, if you get into the details of numerical methods, you would learn how to compute the inverse matrix with a numerical routine. MATLAB provides it for you with a built-in function, or its ability to take a matrix to a negative exponential and interpret that as the inverse. And here, it's got that showing down here how you can use the INV function. And this, as we note down here, is based on a numerical method which is called LU, or lower upper decomposition. All right. So we're going to move on from here, and we're going to introduce the difference between an array operation and a vector matrix operation. So let's pop back over to our command window here, and we will start by clearing this out, clear our variables out, and we'll redefine our A matrix here you should do this too. 156. And if I get ahead of you at all, of course, you know, you can slow me down by pausing the video, right? You can actually make me repeat myself by rewinding the video a little bit. Here is our A matrix, all right? And then we cannot say 1 divided by A, because that says we're trying to divide a matrix into a scalar, and that doesn't work. So if we wanted the inverse of A, we know how to get that. But if we would like to get the inverse of each element of A, what we can then do is do 1 and include a dot with the operator, and that will then take 1 over each of the elements of A. And so we use the dot to indicate that we want the operation to take place item by item and not according to vector matrix rules. When we do it item by item, it's typically then called an array operation, okay? So if I then take a vector B equal to, and let's have that 2, 5, and 8, 2, 5, and 8, and then turn that into a column vector with the apostrophe. And then if I say what I would like to do is do A dot asterisk B, then what I get is item by item. Let's bring A back so you can see that. I get item by item of 2 up here, multiplying item by item in the first row, 5 in the second row, and 8 in the third row. So that is a little bit on the use of the dot operator with a mathematical operator. Now, what I'm going to do is show you how we typically use that. Whoops, sorry. And that is going to be, I'm going to start by defining an x vector equal to 0.1 in steps of 0.1 to 0.9, okay? So that uses those colon operators with an interval of 0.1 going from 0.1 to 0.9. And then what I would like to do is I would like to say for each one of those x's, I want to evaluate a mathematical function and assign the results to y. So I'm going to put in that formula, and it's going to start with a scalar 4, and then it's going to be 0.2 times x. Now what that's going to do is take 0.2 and multiply it by all of those x's in an array, and then add 4 to each one of them, all right? And then what I'm going to do is I'd say I want minus 0.7, and I want that times x squared. Now here, I can't use the caret because it wants to do a vector matrix operation with that. So I use a period caret, which says do the exponentiation item by item. That's the squared. I'm showing a little space there to show you how that operates. And then I'm going to say I would like to do 1 divided by x, but I want to do that item by item, so I put it that way. Now let's see if I've got that right. I think I have. So what it's done here is it's taken all of my x values, and it has shown how they compute to generate the same shape in terms of y values. Now, I'm getting ahead of myself, but if I just was curious to see what's a plot of y versus x, that's what it looks like, okay? So we'll come back to that later. All right. So that little bit, we call this vectorizing a formula, where we take a formula in terms of x and consider instead x as a vector of values or an array of values. And whenever you do that, you then have to be careful how you do these operations that might want to be done as a vector matrix operation, because normally if it sees caret 2, what it wants to do is take an X matrix and multiply it by itself. And for just a vector, that will not work because it's not compatible for matrix multiplication. Okay, so let's pop back over, and we're coming to the end here of the first segment of this boot camp, so hang in there. We're going to pop back over to our slides and move along. And just review, is the use of the dot operators in the case of wanting to take 1 over each element of A with dot divide. And then this was taking 2, 5, 8 as a column vector and multiplying item by item, 2 across the first row, 5 across the second, and minus 8 across the third. And that's how you get that. And then this was the formula up here. I was evaluating the algebraic version of it, and it shows how I do that. And you'll notice when I multiply 0.2 by x, I don't need a dot operator there because 0.2 is just a scalar, so it naturally will multiply each element of x with 0.2. Nor do I need to do anything special with adding a constant because it's just going to do that item. But when I get to exponentiation or divide by, then I need to be careful, all right? So that's what that looks like. And then this is here more or less for information, and that is that it gives a brief summary of some of the functions available in MATLAB, and they're far more than this, but it gives some of the ones that we might use commonly in evaluating engineering formulas, including log and exponential functions, trigonometric functions, converting radians to degrees and back, hyperbolic functions, and then some additional ones down here that relate to real and polar representation of complex numbers. Pi is a built-in value for pi. Eps is the machine epsilon, which is the smallest number that the computer can resolve from another number. And then either I or j, it represents the imaginary unit or the square root of -1. Although in our general chemical engineering calculations, we don't use complex numbers that much, we do get involved with them in control systems work and signal processing work, and so it might come up that you need to use that, and it turns out that MATLAB is very comfortable in terms of working with complex numbers. It's built for it, okay? So let's now shift our gears a little bit, come back over, and think we still have an A matrix, all right? So we'll talk about doing output displays. Now, obviously, if we just type A, we display the A matrix. But one thing that we often do is type DISP-A, which doesn't give us all this A equals header, but just displays the values. DISP short for display. So that is a possible, all right? And then we can have another example just to show you how this can be done, where I'm going to set up an X vector equals, and let's do our linspace 0.1, comma, 0.1, comma, 0.9 in this case. Oops. double row vector. Just a second. Let's clear our workspace. So I'm sorry. We want 2, 4, 6. We want 9 items. I messed you up there. Want to go from point 1 to point 9, and then we will create a y vector which has some other values. These are just sort of some random values, 14.013, comma, 9.012, comma, 7.3303, comma, 6.468, comma, 5.925, comma. Then what I'm going to do is do a space and 3 periods. All right, now that's called an ellipsis, and what it does is it allows us to continue the line on the next line before it executes. And in this case, I'm doing it just so that you can see everything on the screen without it running off the end. 5.925, and then 5.5347, 5.347, 5.2256, 5.2256. 4.7241, 7241. And then I'll close that up, and we'll see that we've got those values, and those are also 9 values. So now what I would like to do is I would like to display both x and y in columns, one next to the other. So I do a little more in terms of my DISP function, in that inside the parentheses I'm going to put in x transpose and y transpose with brackets, and then it will display those values. With a little bit of work here, what I can also do is modify this, and I can have a line first, DISP, and I will put in like a header, which is a bunch of spaces and then X, and a bunch of spaces and then Y, like so. And now I've got 2 statements, and you can see, well, you didn't get your alignment of that header quite right. So let's go back and let's take 3 spaces out of X, and let's take a couple spaces out of Y, and try that again, and it's looking a little bit better. Okay, so you can use this DISP functions to display things in the command window, and that becomes useful when we're writing scripts with the editor and we want to have things displayed as results in the command window. Okay, so we're almost there in terms of our first segment. What I want to do is get over to how we actually format output and input with more control. So one thing that you've seen is that when it displays numbers in the command window, it sort of has a default number of significant figures. All right. So if the default is to display 4 digits to the right of the decimal point, and so there's a command for that, which is format short, and that's the default. And then, for instance, if I say, what's the value of pi, it shows it with 4 digits to the right. And then if I would say format long and let me see pi, then it shows full precision of pi. All right. Now this is the display format in the command window. It has nothing to do with the precision with which the numbers are stored. It's just how they are displayed. So there are others, for instance, I've got format short capital E, and then pi is shown in exponential notation. And then there's a corresponding one called long E, and there are others that we will show you on a slide, all right? So that's sort of controlling the display format, and you can change that, and you can always go back to the default whenever you want, all right? And then what we're going to do is we're going to take a look at how you can control the display of a result more carefully. And here MATLAB uses a function to do this, which is very similar to what is used in the C programming language, or C++. And the function that it uses is called fprintf, and we'll show you how that works. So what we're going to do here is I'm going to create, let's clear our variables. I'm going to create a variable tf, which is equal to 450. And then out here, I'm going to put in a percentage sign, and I'm going to put in degrees f. Now that's a comment. It's shown in green at the end of a line, and you can also put a comment on its own line. And it's useful when you're doing engineering work, chemical engineering work, you're working with numerical quantities to indicate what units you're using, so you can go back and check units and others will understand what units you're working with. So let's make a TC here, and that's going to be equal to quantity TF minus 32 divided by 1.8. And I'll put in a comment here that this is supposed to give me degree C. Okay. And it shows it, in this case, I didn't put in the semicolon, so it shows it as 232 degrees Celsius. Now, what I'm going to do is create a string variable called format spec. That with an apostrophe. And I'm going to put in a percent sign, 5.1f, and I'll explain that in a moment. And then DEGF is equal to percent sign 5.1f C and a backslash n. That is a format specification, and more or less what this means is you're going to display one number with 5 characters and 1 decimal point, a fractional or floating point number, and then there's going to be some text and another number and some text, and the backslash n means go down to the next line of your display. So with that, what I will say here is fprintf, right? And then I will put in format spec, comma, tf, tc. And what I'm doing here is I'm specifying which values go into each of these special format specifications. And then the result looks like that. So I have taken more control over how I'm formatting the output, all right? So that's what that looks like. And let's come back and review that on the slides, and then we'll get up to how we deal with files, and then that's going to be about it for this segment of the boot camp. So let's go back to our slides. So this is the use of the DISP function, and it shows you the examples that we illustrated to you, all right? And how then to include headings if you want. And then these are the options that you have for the display of numerical quantities in the command window, and you'll see that there are quite a number of them. We are typically satisfied with short or short E or something like short G or ENG, which will use the short format but will use scientific notation when the number gets too big or when the number gets too small. Otherwise, it will just show the number. So that's what those look like. And then there's some additional ones, format loose, format compact, which will adjust the output by adding blank lines, which it does, or you can do compact and then it won't show those blank lines that we've been seeing. And then you can go format default to go back to all the default settings, okay? This is the example that we showed you with the fprintf, where we value for TF, computed TC. We showed a format spec, and by the way, instead of using this string variable format spec, we could have put this string with the apostrophes in its place right in the fprintf statement, and then we get our neatly formatted thing. Now there's a lot of details associated with fprintf. This shows how that numeric specification is laid out, and there are other ways to do this than just floating point. You can use integer, for instance, and this gives you an idea of how that is laid out. And then you can go and you can get a lot more information on help, all right? And let's pop back over to the command window and show you how that's done. Way up in the upper right-hand corner, if I type in fprintf, it goes over to MATLAB documentation, and it just gives me an idea of what fprintf can be. It says write data to text file, but then includes the example we used where you just write it to a display, and it goes and it gives you all kinds of information, more information than perhaps you want to see, ideas of how you can work with that. Okay, so we're going to finish up here talking about how we can write data to files and how we can read in data from files, because later on we're going to be using some examples where we have hundreds of data and they're located in a text file, and we want to be able to read that in to an array in MATLAB, maybe get some results and write those results back out to another file. So let's see how we can go about doing that. Let me clear this, and then I'll clear our workspace. And then I'm going to use a built-in function. I'm going to say rn equals n. Oops. What rand_n does is it generates random numbers, all right? And n corresponds to using a normal distribution. And if you don't specify anything else, then the random numbers will be with a mean of 0 and a standard deviation of 1. And it's going to generate 5,000 of them rows in one column, all right? So it's going to do that, and what you can see here is that it has shown that over here, and if I double click the spreadsheet, it will show me the beginning of that, and then this goes down 5,000 deep, all right? MATLAB does not mind working with large quantities of values, although you ought to be careful not to display them in the command window, or they'll be going on for a very long time. So then what I will do is I will define a format spec again. That's a typical way to do this. And it's going to be $, 10.8 F \n. What that means is it's going to save the number in a field 10 digits wide with eight digits to the right of the decimal point, which is a pretty highly resolution way to, and then between each element, it's going to move to a new line, all right, or a new record in the file. And then we're going to create something called file ID, and we will do for that a function called fopen to open a new file, all right? And I'm going to give it a name, test data, and I'm just going to throw a 1 in there to distinguish from something I've already done, txt, for a text file, test data, all right? And then I'm going to put in an action desired, which is W, which means write the file, all right? So that opens a file for writing, all right? And then what I want to do is actually write data into the file. So I do my printf for that, and I use my file ID now, all right? And then I use my format spec, and then I use rn for my 5,000 random numbers. And I write that particular file. Now I will have a file out there called testdata1. Should be in my list down here on the left. Here it is, testdata1. And that file will have all 5,000 of those numbers, okay? Now, let's say I'm going to skip over one element here and come back to it. Let's say that I then want to read those numbers back in, okay? Let me clear the workspace for right now so we don't have anything over here to the right. And then I'm going to do a format spec, which is more general, to %f in apostrophes. That just means try to read in a floating point number. And we're not specifying the format in which that number is stored. We just know it's a floating point or decimal fraction number. And then the file ID is going to be essentially the same thing that it was before, with one difference. And this is fopen, open the file. And it's testdata1.txt. But now it's R in apostrophes because we want to read from the file and not write to the file. And then we can say something like, my random numbers are going to be equal to now scanf, not printf, of my file ID and my format spec. And what you can see over here is that we now have an array, 5,000 rows, one column, that contains the random numbers read back in from our text file. Okay? So that's something in terms of doing that. And then the final thing I want to illustrate in terms of input here is how to ask the user for data, right? And so let me pop over to the editor for this, if I can find it. Here's my editor, and I'll click on the plus sign to make a new script. That script, I'll start out, the first command I'll do is clear, and then CLC to clear the workspace and clear the command window. And then I'm going to put in X is equal to input, and I'll put a string, enter a value for X, colon space. And then I will put in something like ANS for answer is equal to input, and I'll do something a little different, and I will say enter Y or N. In other words, now I'm interested in a text or string entry, not a numerical entry, and then I qualify that by using S in apostrophes there, which indicates that I want the user to put in a text answer of the letters Y or N. So we've got that. Let me save this, and I will call it input function examples, just so it's saved, and then I'll run it. And over in the command window now, it says enter a value of X, so I'll put in 22.5, and then enter Y or N, so I will put in Y. And so it has entered those two values, all right? And it shows them over here as my answer is Y and my X is 22.5. So you'll see us using as we go along the input function for allowing for user input. We'll illustrate that, and that will be useful to us. The final thing that I want to show you here is that one thing that if I have done a bunch of work and I have a workspace with a lot of values in it, and I would like to come back in a later session and start where I left off. Well, we don't have very many values here, but what you can do is you can just do save and then put in a name, my work, whatever. And then it will save that, and then you can get out of MATLAB, you can come back another day, whatever, you can come into MATLAB, and as long as you have the right path up here to where you are looking, for the moment, let's clear the workspace, and then let's do load my work. And it brings back the values that I had, all right? So let's wind this up by going back over to our slides. This shows how we printed out to a file those 5,000 random numbers, all right? That shows how we did that. And then shows from Notepad, shows the start of that file that goes 5,000 lines deep. And then this was the use of the input function, where you can do it, if you do it without a second argument, it just expects a number. If you do it with something like S, then it expects a letter or a string entry, and it just shows a little bit on how we do that. The next part of the boot camp is that we're going to start looking at the way you go about programming MATLAB with like if statements and for loops and things like that. And we'll move on from there and get into making plots and making separate MATLAB functions. But I think this is enough for now. I need a break, and why don't you take a break too, and then we'll see you back in the next video.